Alrighty, so we're now doing shapes and we're doing what's called the VESPR theory. How do we know with all our different non-metal compounds what shapes they form? So we use this little scaffold, and I'm going to go through an example with it, but we go around the central whatever atom, so with carbon dioxide would be the central carbon atom. There are so many pairs of electrons, some are bonding pairs and some are non-bonding pairs. Bonding pairs are the ones involved in the covalent bond, non-bonding pairs are the ones which aren't. So if you remember when we talked about H2S, what it looked like was this. And so therefore we had 4 non-bonding pairs of electrons. That are 2 non-bonding pairs of electrons, 2 pairs of electrons that weren't involved in the bonding. Then you say these electrons are arranged into a shape which minimizes repulsion around the central whatever atom, resulting in a whatever shaped molecule according to VESPR theory. Don't worry if this is all sounding like a different language. You will get the hang of it, I promise. So that's where the shape goes. When we talk about shapes, that's where that shape is going to go. Don't have to copy that down, but do copy down the scaffold. So if we have 2 lone pairs, so not 2 lone pairs, no lone pairs. Lone pairs are the ones which are non-bonding. So lone pairs, that is the same as non-bonding. I'm just going to call it NB, so if you want to copy that down. So if we have an atom and we have no lone pairs, which means that everything is bonded on my atom, that is going to give me, and I've only got 2 electron dense areas, so I've only got 2 bonds, that means that I will have a linear shape. So that's our H2S again. I've only got 2 electron bonding areas because I've only got 2 hydrogen atoms. That's going to form a linear molecule, straight line. I have no lone pairs. If I have if I have then 3 electron areas, so I've got 3 bonds going on, 3 bonds, and I have no lone pairs, I get a trigonal planar one. So that means if you were making in 2 dimensions, it's on a plane, it's on a piece of paper, it looks like a pyramid, almost. So you've got your central atom there, and then you go up to another atom down there, and then you go across to another atom over there, and then you go to another atom over there. So that's trigonal planar. And that middle one there, of course, is the central atom, but that's when I've got no lone pairs. If I have those 3 regions of electron energy, and that's not necessarily 3 bonds, because something like water, I have oxygen and I have hydrogen and 2 hydrogens. They should be straight, but I'm just trying to do it without clicking too much. And then I have 2 lone pair electrons up there. So if we look at that, and my pen colour is for cyan, there's a lone pair. That is a lone pair, so that's one region of electron density. A lone pair is a region of electron density. A bond is another region of electron density. This time I have 3, but this is actually a bent shape. Those lone pair has quite a lot of repulsive force, so it pushes these 2 together somewhat. Okay, so they're a bit closer than they would be, but that causes a bent shape of a molecule. Then if I have 4 regions of charge, so in this case I either have 1 lone pair or 2 lone pairs or no lone pairs. If I've got 4 regions and I don't have any lone pairs, that will mean I actually have something that looks like this. I actually have 4 single bonds. So methane is a good example of that. We drew it out flat, if you remember in the last video. But what it would actually look like is C, and then we'd chuck up there to H, and then we'd have out here, down up the back, if you like. We'd have another H, sorry for the annoying clicking, and then you'd have another H down there, and that's my best impression of 3 dimensions, but that's called a tetrahedral shape, where we've got those going in 3 dimensions. Now, if we then have one lone pair, but 4 regions of electron density, so a lone pair and then 3 bonds, something like NH3 is that. NH3, nitrogen, has 5 electrons. It's only bonded here to 3 hydrogens. So that means that it's got a lone pair up the top, and it's got 3 hydrogens, which is sort of spread out in this pyramid shape, and that's called trigonal pyramidal. So it is very much like a pyramid, it just has this lone pair up the top. In fact, it's exactly the same as tetrahedral over here, it just doesn't have that bond, it's got a lone pair instead. Now, if we get something like this, where we've actually got 2 lone pairs, then it's really bent, and those 2 electron lone pairs up here really push them close to each other. Okay, so it's really, really bent. Then there's a lot of different ones as well. If we've then got 5 regions of electron density, 1, 2, 3, 4, 5, we get what this is called a trigonal bipyramidal shape, and that's basically you've got 3 atoms in the plane of the central atom, which is the ones you can see here. So that one, and that one, they're sort of all in the same horizontal plane, and then you've got 2 vertical ones as well. So you've got 2 ones in a vertical plane as well, that one and that one. So that's called trigonal bipyramidal. If you're doing it with 8, you get it into like an octagonal one. So you've got octahedral, this is called. Now, with an octahedral one, this is 6 regions of electron density. So it's a little bit confusing because you automatically think octahedral, therefore 8. It's not, it's 6. So we've got 4 in the plane, 4 in the plane, and then 1 up above and 1 below. For now, I'd just like you to concentrate on those ones. Alright? So do concentrate on those ones. Don't worry, but you do need to know the names. So that this is trigonal planar, that's tetrahedral, that's trigonal bipyramidal, that's bent, that's also bent, that's trigonal bipyramidal, and that's octahedral. It's linear. Okay? VESPR theory. So let's do an example, and this is using the scaffold that we talked about. So ammonia, and ammonia, if in case you don't know, is NH3. We've talked about ammonium, which is the ion of ammonia, which is NH4+. So we go around the central atom, so the central nitrogen atom, because there's more, it requires more valence electrons. There are 4 electron pairs, 3 bonding pairs, and 1 non-bonding pair. So you look at this down here. This is ammonia. It's got 3 bonding pairs, 1, 2, 3, and it's got 1 non-bonding pair up there. Then you go, your whole blurb. These electron pairs are arranged into a shape which minimizes repulsion around the central end atom, resulting in a trigonal pyramidal model according to VESPR theory. Again, something that you need to memorize. Don't worry about this angle. But how do we know it's trigonal pyramidal? Well, remember, it's got 4 electron pairs, but 3 are bonding and 1's non-bonding. If we go back to here, it's got 4 electron pairs or 4 regions of electron density. 3 are bonding, 1 is non-bonding. So if it's 1 is non-bonding or 1 is a lone pair, that's a trigonal pyramidal shape. Okay, so practice makes perfect with this. There are some questions that would be good to do to help practice this one. So you should be able to tell this by now. Are these statements about covalent bonding true or false? Atoms bond to half complete the outer shell. That's false, fully. Non-metals rarely form covalent bonds. Very false. They often do. Covalent bond is a shared pair of electrons. True. Oxygen molecules contain a double bond. Think about that. But yes, it's definitely true. Sodium chloride contains covalent bonds. No, it doesn't. It's ionic because sodium is a metal and non-metals. And covalent bonds only occur in compounds. That's false. We'll talk about that more later, but you can get something called a covalent network, which is lots and lots and lots and lots and lots of non-metal atoms bonded together rather than just a few. Okie dokies. Now think about the difference between covalent and ionic bonding. We talked about that right at the start of the first video on this covalent bonding topic. Thanks.